Okay, hello there. So welcome back. So we're going to finish this problem. Okay. So what you see over here, we finish off with second moment of area. So the formula we're going to use is stress X is equal to minus my over I. I put a minus over here is because we're going to induce a what? A compression. Okay. So from here, second moment of area, if someone asks you what do you mean by second moment of area, it's also known to resistance to bending. Okay. The higher this I value is, the more resistant is to bending. So I'm going to give you formulas for it. So I for solid shaft, okay, is equal to pi over 4, right? Pi over 4 multiplied by radius, outer radius, power of 4. Okay, so that is for a solid shaft. Okay, and then we also have I for hollow shaft. So it's equal to pi over 4. Okay, R outside power 4, radius in the outside minus by internal radius power 4. Okay, so these are the formulas that we should be using, okay, to calculate I. Right, so now we have all this information now. Okay, now we have all this information now. So we are going to deal with static analysis. Okay, static analysis, okay, means I'll explain what do I mean by static analysis. So we're going to carry out static analysis to find the force acting, the force and moment. Okay, the forces and moment acting at point H. Okay, or element H. Okay, so we're going to have a shear force. Okay, so we can always at element H, we can always assume a shear force V at point H. Okay, we're going to assume it downwards. Later on, if it changes, okay, you just change the arrow. If the sign is minus, you change to up. The sign is plus, keep it as it is. And then we're going to assume moment in the anti-clockwise direction at point H. Okay, so we're going to find the moment first. Okay, or the forces. So positive forces going upwards in the Z direction is equal to 0. Why Z direction? Because this arrow is, this transformation is Z, right? So this will be equal to 600, okay, minus 600, right? Minus VH is equal to 0. The shear force at point H is equal to 0, right? So this is where the first 600 come in. And then we have the second 600. Why is it minus? Because the second 600 is in the minus sign, or is coming down. So coming down means minus, going up means plus, as what the sign says over here. Okay. And then the next one is we're going to take some mention about moment, right? So the rotating axis over here is what? Y axis, right? Okay. So moment Y, and we're going to take moment at point H is equal to 0. So we're going to take moment. So point H is over here. So this is our point H, right? Right. So we're going to take our moment over there at point H. Okay. Then we can start calculating. Okay. So what this size means is anti-clockwise is positive, clockwise is negative. Okay, so the first 600, which I'm going to highlight, right, from point H, which I highlight, the 600 will generate a clockwise moment, right? It's going to generate a clockwise moment over here, right? So 600. So if it's clockwise, so it's minus 600. And then times by perpendicular distance is equal to what? Times by 6 plus, right? And then the other one, the other 600, the one that I'm going to highlight now in blue, okay, relative to point H is going to do anti-clockwise. So anti-clockwise, like what the sign over here say, is plus by 600 multiplied by 8. Okay. And then plus, you have to include the moment about H down here. Okay, the moment. Okay, so it's anti-clockwise, so it's positive. Okay. And the whole thing is equal to 0. So moment about point H is equal to 600 times 14 minus by 600 times 8 is equal to positive 3,600 Newton meter, no, pound inch. Okay, so 6 plus 8, 8 times by 600, yep, 3,600. So when this is positive, what you see over there is positive, means this direction is correct. Okay. If it's negative, means it's in the opposite direction. If it's positive, don't change the direction. Okay. So this is valid. Okay. So from here, we know that if this is turning this way, the moment will also be, the counter moment will be over in that direction they've just drawn. So that's where the element H is under what? Is in compression. Okay. So now we can calculate this. What we can calculate is stress X for element H is equal to minus moment about point H Y divided by I. Okay. So this is equal to minus 6,400, right? And then the Y, the radius of the shaft is what? The radius of the shaft are we given? 1.25. Okay, so it's 1.25 divided by 2. Then I, because it's a solid shaft, is divided by pi over 4 multiplied by the radius. Okay, so it's 1.25 divided by 2 power of 4. Okay, so this will be equal to 6400 times by 1.25 divided by 6400 times by, hey, why 6400? Eugene, wakey. 3600, do apologize. Right, so it's equal to 3600 times by 1.25 divided by 2. So it's 2250 at the top minus 2250, right? Divided by 1.25 divided by 2 power 4 times by shift pi divided by 4. This is 0.11984. Let me do it again. Okay, power 4 times by shift pi divided by 4. Yep. So this will be equal to 3600 times by 1.25 divided by 2. So this will be equal to minus 0.11984 is equal to 18.775 times 10 to the power 3 psi. Okay, let me do it again. 3600 times 1.25 divided by 2 divided by shift pi divided by times by 4 divided by 1.25 divided by 2 power 4 is equal to 18.775. Okay, so this 18.775, what we just found is this. Okay, if we go back to our element, all right, we go back to element, we have just identified that we have a compression, right, going at minus 18.775 0.5 times 10 to the power 3 psi. Okay. So what you can see over here is the bending stress will induce a normal stress. So, sorry, the bending load, I repeat again, the bending load will induce a normal stress. Okay. Then from here, we're going to calculate the shearing stress. Okay, we're going to calculate the shearing stress. Okay, so we have found, we are going to next.
Sir, just could you scroll down for a bit so I can copy the
Yep.
notes?
Yep. So now we found that the normal stress is equal to minus 18.775. Okay. So I think I need to draw this also so you guys can see better. Okay. So this 600 is for this one, and this 600 is one. Okay, that's why we multiply by 8 the distance.
Sir, just asking, where did you find the value for RO?
Oh, it's given in the question, right? So the RO, the radius, the diameter is 1.25. Can you see that? Right? Can you see the diameter is 1.25? Yes or no?
Yeah, it just wasn't part of the the screen when you were
Yeah,
writing that
I know. Okay. Let me see, can I make the screen bigger for you? Yeah. Okay. Okay, now the next thing that we're going to do is we are going to look at shearing stress. Okay, so shearing is not difficult to understand. It's just again plugging in to another set of formulas. Okay, to another set of formulas. So what we want to do now is shearing stress. Okay, so the shearing stress is induced by the torque acting on the shaft. Okay, it's a torque. So what is torque? Torque is equal to force times radius right? And it's different from moment. It's not the same. Yeah, moment is perpendicular distance. This is by a radius. So if you look at our problem, right? If you look at our problem, the 2,500 is the torque. Okay, the 2,500. So the torque is different. The torque will twist, right? The torque will induce a twist on the shaft. Means the shaft will still look round. Yeah, the twist. Once you get a twist, the shaft will still look round. Whereas bending moment, okay, bending moment, right? The normal stress bending moment is going to induce a banana. Yes or no? Right. Whereas a twist, right? The shaft will still look round. Okay, so that is the difference between a torque and a moment. Okay, moment is force times perpendicular distance. The torque is force times by radius. Okay, so from here, okay, so we know that